Hello, everyone. Welcome. So, this is a presentation I prepared to tell you about some things not everybody knows they're possible to do in materials. Some are optimizations, some are more like special effects, but they seem to be not well known. So I wanna help more people get to know those features. So let's get started. The first one is optimization thing. First, let me show some stats here on the screen. Stat scene rendering. All right, so here we have the mesh draw calls is currently being reported as 10 mesh draw calls. And I have all of these spheres, so it would be more than 10. But Unreal has an automatic optimization that makes several objects that use the same material be rendered as one or as few as possible. And this optimization is on by default. I think it exists since Unreal 423 or 424, and is on by default. But there are some ways of doing things in materials that can break this optimization. And this is an example of that. So if I hit play here, you can see my mesh draw calls count went up to 49. And that's bad. Of course, that's bad. But that's because I'm setting the colors in these spheres. They all have the same material, but I'm setting their colors with a primitive with a color parameter. And the color parameter, any kind of parameter actually, when you set it to set it, you have to create a different instance of that material, and then you can set the parameter. When you create a different instance, Unreal can't optimize the rendering by rendering two meshes with the same material anymore because there are different instances. If one is red and the other is blue, they have different settings. They can't be rendered at the same time. But if you send that information directly to the video card and say, hey, these are the same material, just change the parameter for both of these meshes. If you send the different colors as information in the mesh itself, then you can have the same material. And the material is going to read the information from the mesh. And this is possible in Unreal. So how do you do that? I'm going to stop here. And I'm going to show you first what happens when you use that optimization. So here I am setting my colors via material dynamic instances. Now I'm going to set them via something that's called primitive data. So I'm going to simulate again. And as you can see, the draw calls went down even. So they're now 8 instead of the previous 10. And this is, thank you, Enrique. This is really good for optimization because now you could have like hundreds of meshes with one draw call for all of them. And these are 8 because of the other things in the scene. Lights count draw calls, the plane, the sky that's behind it, everything. But still, 49 against 8 draw calls. That's something, huh? So now, let me show you how I did it. First, you have to set it up in the material. So my material, I have the same material, but I have both settings here. The color via the way we always did it before. So a vector parameter, then I was setting the color through it. But I have a scheme here that when I activate this when I set this to 1, I interpolate to use the color from something that's called primitive data. And primitive data are like, it's like an array of floats that's set in your mesh, not in the material. And the material reads from the mesh. So you just have to say, hey, I want to use this index for this variable. So for instance, my use primitive data here is set to use index 4. So what you do, you create a parameter like this, then you activate this, use custom primitive data. Now you have to set what index it uses. So if I start this vector, for instance, on index, let's see one that's free, 5. It's going to be using index 5, 6, 7, and 8. These are going to be the channel red, green, blue, and alpha. So this vector here is using those channels starting from 0. So 0 is red, 1 is green, 2 is blue, and 3 is alpha. Then the way to set it via blueprints, I want to save this. You go to your blueprint. You get your mesh like this, static mesh component. Here I'm just getting the spheres from the scene. Then I get from each of them the static mesh component, and I call set custom primitive data float. Here I'm setting the index 4 because this is my parameter that decides which type of color I want to use, the one that's a standard parameter or the one that's primitive data. So I'm setting it to be the primitive data. And then I set the color with this node, set custom primitive data vector 3. You have others too, but for the color, I'm just using this. I just need the color. And then I'm setting a random color to every sphere. And just as you can do with normal parameters, you can animate these. So I'm not animating in the blueprint itself. I'm animating it in the material by using this hue shift node, and then I pass time as the how much to shift, so it changes the color in a cycle. But because I'm changing something in the mesh, not in the material, and it's something the video card can still recognize it as the same mesh, just with some different parameters, Unreal is able to merge all the draw calls from these spheres into a single draw call. So instead of 49 draw calls, you have only 8. Nobody told me I wasn't doing it on my main screen. So let me show that again. The material is set up by activating this option here, use custom primitive data in the vector. On the parameter, you can also do it to floats. And these settings, you can only do them for things that are floats, okay? You cannot do this with textures. If you have different textures for different materials, or just different instances with different textures, it's not going to be merged together. It's not going to be the same draw call. You can only do this with floats for now. So this was the setup in the material, and in the blueprint, this. Get the static mesh component, set custom primitive data float. I'm using this to set that scalar that decides which parameter I want to use, and I'm using set custom primitive data vector to decide the colors. Okay, so this is the first trick. Second trick. You can, let me clear this. You can manipulate UVs in your materials. So let's say you modeled your mesh and you want to scale the UV. You don't have to do that in the mesh UVs itself and then re-import into Unreal. You can do that directly in the material. Scale, move, rotate. So let me show you. For instance, here I can flip my U coordinate. So now it's flipped. 0 is on the right side here. 12 is on the left side. I can flip V. So now black's at the top. So I can do this. I can do both at the same time. See? But this is doing both at the same time, flipping both axes is just like rotating 180 degrees. And I can rotate 180 degrees with this angle variable here. Same thing. But this works for any angle actually. So I can rotate my UVs. I can decide if they tile or not. So for instance, I have this vector parameter here to control U and V offset and U and V tiling. And I can offset on U, offset on V, and it changed the timing. So if I put this back to 0 and increase the tiling, the material repeats, that's tiling. I can turn off the tiling. So now the material is not repeating. The texture, not the material. So the texture is not repeating, and its borders just get clamped. Now let me show you how you do these manipulations in the material. So let me just put these back to 1. All right, so in the material, to rotate, you have a rotator. You pass your coordinate. I'm passing texture 0 here. I don't have to. If you pass nothing into this node, it still works the same. I'm just passing the coordinate because if I want it to be something like UV coordinate 1 or some other UV set, I can control it. Then you need to pass into the time. Oh, also for the rotator, you have to set speed. For this to work the way I did here, you have to set speed to pi times 2. And it's easy in Unreal. If you don't know pi by heart, you can just type pi here. There's a pi node. You go into that. Here's pi. So you copy it from here. Then you can pick the rotator, paste it here, times 2. You can do math in these number inputs in Unreal. So you can do this. Now I have pi times 2. All right, so once I have pi times 2, I can control my rotation from 0 to 1. So 1 is 360 degrees. So what I did here is I have my angle. That's going to be an input from 0 to 360. Then I divide it by 360, which means that if the user inputs 180, it's going to become 0.5. If the user inputs 360, 360 by 360, 1. So this is the angle transformed in the range from 0 to 1, and then I pass it into the rotation with speed set to 2 pi. So that's how I rotate the texture. Then, in order to make the flip, I have these static switch params here. So if you want to create a static switch parameter, then you can have something that's true or false, and what's going to be used it depends on what's connected on true or what's connected on false. So for flip U, if it is true, I use -1, and if it's false, I use 1. Same for flip V. But then I put these 1 or -1 together in a single float 2. So float 2 means it's like a vector that has R, G, B, or X, Y, Z, but it has only 2 numbers. So it's like a UV coordinate that has only U and V, X and Y, or R and G. All of these are the same thing. They're just a group of numbers. So I put them together. So I have like X and Y, or U and V. And I multiply them by the UVs. So multiplying UVs by -1 is the same as flipping the UVs. Then after I flip the UVs, I subtract the offset from my vector parameter here, UVs. By the way I did these have names is when you select this parameter, if you go here to parameter customization, you have channel names. So you can set your custom name to each channel. Instead of being just like red, green, blue, and alpha, you can set your own custom names to them. So I subtract these offsets. That's going to move the coordinates around. And then I multiply them by the tiling that the user set, which makes me see more of the texture repeating, if the number is big, or less if the number is smaller. So imagine that you have your UV. Let me show you in practice. Shift P. I have Shift P set as a shortcut on my project settings to show previews, so that's fast. All right, so I'm previewing the UVs of this cube here. So they start at 0, 0 here, 0 on X, 0 on Y, and then they are 1, 1 here. They are 1 on Y here, and 0 on X. That's why it's green, because Unreal displays UVs or any group of 2 numbers as red and green. So at the top here, I have 1 on red and 0 on green. And that's why you see these colors. These are the UV coordinates. Now, if I multiply them, this is what happens. I'm going to multiply by a smaller number, so 0.5. When I press enter, what's going to happen is this is 0. 0 times 0.5 is still 0. So this is not going to change, this corner. But this one here is going to change because this is 1 and 1. 1 times 0.5 is 0.5. So that's going to become darker. I don't know if you can see it really well. Let me put it on unlit. Unlit, it's really noticeable. So 0.1 to be more drastic. So it becomes very dark, which means this corner here is 0.1. And if this corner is 0.1, you're seeing like a very smaller piece of the texture it would have in your material instead of the whole texture, because the whole texture is from 0 to 1. Now, if I do 2 or higher numbers higher than 1, you see that from here on it's yellow, because Unreal can't display this in colors. But this would be repeating the texture, because now I have from 0 to 1 and from 1 to 2 here, which means the texture is going to be repeating. Anytime you go higher than 1, the texture starts repeating. And you can see this if you do frac. Frac is a node that displays only the decimal part of number. So if you have 1.02, it's going to be 0.02 only. If you have 1000.5, it's going to be 0.5. It doesn't matter what's behind the decimals. It's only the decimals. So if I preview this now, you can see this is going from 0 to 1, and then I have the decimals again from 0 to 1. So that's how tiling textures work. And then I choose if I want to tile or not. And the way I do that, if I want to tile, I just use it the way it is, because textures, they tile automatically. But if I don't, I use saturate. Saturate is not something that changes colors in the way it sounds. Saturate clamps values from 0 to 1. So if you have something that's less than 0, it's going to become 0. And if you have something that's greater than 1, it's going to become 1. And when you do that to UV coordinates, you're clamping the texture, the UVs, to 0 and 1. So anything higher than 1, where the texture would start to repeat, it's just 1 all over. So you're just seeing the texture clamped. You see the corner of the texture. So that's why when I turn off tile here, like it is off now, and I try to repeat the texture, it doesn't repeat. It shows the last pixel of the texture, which would be coordinate 1, repeated again and again. But if I turn tiling again, turning tiling on again, then you can see the texture repeating. So this is UV's manipulation in materials. Now let's go to something else. Texture projection. I have 2-3 videos about this in my YouTube tutorial going into detail on how to implement this, so I'm not going to explain all the math. But I want to show you that it's possible, because it's cool. Sometimes you just want to have a texture on top of your mesh, and it doesn't matter how the mesh is UV mapped, is unwrapped. You just want to have it on top of your mesh as if it was on the screen. So that's how I have my texture now. You can see the texture is following the screen of the objects, but it's still just on the objects, as if the objects were a mask for the texture. This is what we call screen projection. Screen projection is very simple. You just get the screen position, then there's a viewport UV setting, and this is just the UVs of your screen. So if I make the object occupy the full screen here, you're gonna see it's black in this corner here and yellow at the bottom. And then I'm multiplying by a size. Remember, multiplying repeats the texture, so I'm multiplying by 2, I'm repeating the texture twice. And then I connect it into the UVs of my texture. So that's it. That's all you need to do to make this screen projection effect. Now there's another effect I can show you. Let me pick these meshes and apply world projection. Now world projection is kind of like the screen projection, but instead of using the screen, it uses coordinates from the world. So what matters is where the object is in the world. So if I move this mesh around, you see the texture, besides the motion blur effect that happens in Unreal, the texture is not moving with the cube. It's like the cube is moving through the texture, because the texture is being mapped by world coordinates. This is very useful for terrain, so you can have a texture repeat all over the terrain, so you don't have to worry about the UVs in the terrain. But it can be bad for walls and things that are really vertical. Of course, this is because I'm using the coordinates from the world. There are X and Y. I could use other coordinates, like I could use just X and Z. But what would happen is my texture would be projected on the side and then stretch it along this side and this side. So you have this compromise. You choose one side and the others are going to be stretched. The way to do this projection is you get the absolute position of your pixel. So this is the position of the current pixel being rendered. Then you pick two coordinates from the world. In this case, I'm getting RNG, which are X and Y. So the two coordinates that make the floor in Unreal, X and Y. Then I divide them by the size I want the texture to be. This is going to be size. Since these units are in Unreal units, which are centimeters, this size is relative to that. So if I divide it by 100, it means that the texture is going to repeat every 1 meter, because 1 meter has 100 centimeters. So if I increase this, for instance, you can see the texture becomes bigger. So, and this is what I said before. If I choose, I could do X and Z coordinates, and now my texture is being projected on X and Z, both sides, but all the things that are perpendicular to that projection just get the texture stretched. So it's very useful for terrains when you use X and Y. And that's all you do. World position, pick two coordinates, divide by the size you want the texture to be, and that's it. Now the third one, and the one I'm not going to go into much detail, I just want you to know it exists because I have a video about it, and it takes a while to explain how it works, is the Tri-planar projection. Now the Tri-planar projection is just like the world projection, as in the texture is in the world, not in the mesh, but it's Tri-planar. It means it projects 3 planes of texture onto your meshes. So you have texture on all sides of your mesh. Doesn't matter the shape of it, where it is, you have texture on all sides. It defines what projection to use depending on what direction the mesh is facing. So this, you can see this there's like a blend between the top projection and the side projection. Right here, there's a blend. So the Tri-planar, you do it like this. Here, Tri-planar projection. Like I said, I'm not going to go into detail because I have a video about it, and it takes a while to explain everything in detail. But you get the normals, then you do some math with the normals to know what projection you should use. It's like creating a mask for all the 3 projections from the normals. So first you create the mask, and then you use that mask to filter the projections, the world projections of the texture. So I have the top, a side, and another side projection. And this is the same logic as world projection. The only difference is that I'm using 3 combinations of coordinates from the world position to make these 3 projections. So green and blue, red and blue, or X and Z, and then X and Y. Then I mix them using the masks computed from the normals, and then you have Tri-planar projections. It's really cool. And if your mesh has no UVs at all, this is the way to apply a texture on it in a way that looks good. It looks like that it makes sense. And something else you can do with these, like if you want the texture to stick to your mesh, you can use this transform vector from world space to local space on both your normal and your world coordinate. And I have a toggle for that in my material. Where is it? Tri-planar projection. Let me just apply it. So let me see. Local space. So if I turn that on, now the texture follows the mesh. And even if I rotate it, it still works. So it's like the mesh was correctly UV'd, but it's not. I mean, the GIF is, but I'm not using its UVs. Just like this, I'm not using its UVs. So that's really cool for meshes. Like if you create a procedural mesh from code or blueprints, you don't have to create the UVs if you use a material like this. It's a bit heavy because you're sampling 3 textures for each texture. Like it's going to be 3 textures for base color, 3 textures for roughness, metallic, etc. 3 textures for normal. It's heavier, but it gets the job done. And nowadays, like it's heavier, but it's not like, oh, it's not going to run. No, it runs. It runs and it runs fine, especially on these 30 series. Another trick. Let's go to the next one. Now this one, Every time I see people wanting to rotate their meshes over some period of time, constantly rotating the mesh, they do it on tick, on a blueprint. That's the way to do it. But if you just want to rotate the mesh, you can do it in the material. Let the GPU compute the rotation, and then you're saving a lot of processing power because the GPU does that. Like, GPU eats triangles and pixels for breakfast. So it's like you're paying no cost at all. And the way to do it is Unreal has some nodes for you. You don't even have to really figure out the math. The one to rotate is rotate about world axis. I'm using the cheap version. It only allows me to rotate on X, Y, or Z. If you want some other vector that's not one of these three perpendicular ones, you're gonna have to use a different node and kind of make the math for yourself. But if you just want to rotate it in one of these three axes, this is the cheap one. It does the computations in a different way that's lighter than the other way. And it only requires you to set the rotation amount, which I'm using something from time, so it changes over time. So I keep rotating the mesh. Then you have to set the pivot point, and you can get the actor position in your materials. So that's the pivot point for my mesh. And the world position, it requires the position of the vertex that you're rotating. If you get absolute world position, that's the position of your vertex. So something that happens in a real material is some outputs here, some of them are being executed in the vertex shader of the material. The material has a vertex and a pixel shader. The vertex is something that executes only for every vertex in the mesh, and for every vertex in the mesh. And pixel shaders execute for every pixel in the screen. So everything you can do in the vertex shader is usually faster because you have way more pixels being rendered on the screen, especially when the mesh is full screen, than you have vertices being computed. So this runs on the vertex shader and it's rotating the vertices. But because you're rotating the vertices, let me break something here. Because you're rotating the vertices, rotating the whole mesh, the normals, the thing that says what direction the surface is pointing at, also rotates with it. It rotates, actually it doesn't rotate. The problem is that it doesn't rotate automatically. So you're rotating the vertices. Let's say you have a normal here. And this fake sphere here is my mesh. So you're rotating it, but the normal is like still pointing at the same direction, always. Like now I'm pointing at the camera. It's always pointing at the camera, and the mesh is rotating. So it should rotate with the mesh. Now the way to fix this is to use this node here, fix rotate about axis normals. Then you pass in the rotation axis. Since I'm using the z-axis here, z is up. So I'm passing z to the rotation axis. Then the rotation angle, which is the same thing that you pass to the rotation amount here. And the rest, pivot point, etc. By default, they are the same things I did here. So absolute world position is the world, space, vertex. Actually, this is not the normal. The normal would be the vertex normals. But that's automatically set to this, so I don't have to, unless I want to set some custom normals for some reason. Movement mask, I don't have to set it. It's something that like you want some pieces of it not to rotate the vertices, but I want the whole mesh to rotate, so I'm not using it. And pivot point, if I'm not mistaken, pivot point is by default the actor position. No, pivot point is 0. Oh, but it's 0 off the mesh. No, wait. No, it's just 0, but it doesn't matter. I don't know why they put they let you set the pivot point in this function, because it doesn't matter for normals. It really doesn't. You can set anything here. It's not gonna make a difference, but they did. So that's why I got confused for a while. And then what I'm doing is this. I'm passing the new tangent space vertex normal, which is the normal corrected after the rotation, into a vertex interpolator, and then to the normal. This fixes the normals. Why am I using a vertex interpolator? Because the vertex interpolator lets you compute things in the vertex shader, not the pixel shader. So it means that instead of computing whatever is in here once for every pixel, I'm only computing it once for every vertex in the mesh, which is way faster. even if the mesh has a lot of vertices, usually you have less vertices than you have pixels on the screen. So this is how I do this transformation. Oh, and there's another thing. This is really important. If you select the material, let me show you. This is the normal that gets output from that computation. So these are the normals being rotated. And as you can see, this is not like a normal map, pun not intended. Because those normal maps, they are usually mostly blue with some red and green. This is not, because this is a world normal map. It's in world space. So it tells what directions the mesh face in world coordinates. Now, these materials by default, they expect tangent normal maps, which are the blue ones, the mostly blue ones. You have to turn it off. Oh, this is tangent space vertex normal. So yeah, that's the tangent thing. And if you actually forget everything I just said, I'm confused because this is something I had to worry before. But now that they have this tangent space vertex normal here, it just works if you plug it in here. And then you can mix it with other normals. So yeah, you don't have to worry about it. What you would have to worry is if you were using this setting here, new world space. See, this is what I was talking about. Tangent space, I should have read it. Tangent space is already the one this material expects. World space is the one that if you use, this is world space. All right, now you see the normals rotating, and it makes sense. And you would have to turn off tangent space normal. So if you turn off tangent space normal, it's going to be useful for other things as well in the future. If you turn this off, now the material expects world space normals, and then this still works normally. But if I leave that as the default of on, now everything's broken because I'm passing world normal coordinates and it needs tangents. So that's how you rotate a mesh. I'm sorry for the confusion with the tangent thing. And there's something else I have in this level. So I have this plane here, and this plane follows my camera no matter where the camera is. It's always facing the camera. And this is something I didn't have to do in blueprints. And this is the better way to do it because I don't have to compute anything in blueprints. So I do it in the material too. So I have my material here, M face camera. And M face camera uses this node, aligned mesh to the camera. This is some matrix math that Epic did for us. I didn't do this function. This is already in the engine. You can use it. And this makes a mesh always face the camera. Actually, it makes the mesh follow the camera rotation around. So it's not gonna make your mesh face the camera by default, just you using this node in your material. You have to know how to use it. You have to know how to set these object bases here. And this is the thing that it took me the longest time to figure out. So this plane here is the standard Unreal plane. Let me show you how you set those bases. This plane has, the front of it is Z. So if this is now local space. So if I rotate the plane, you can see the transform, the gizmo is still going with the plane. So it's the space of the plane here. So for this plane to be facing the camera, I have to use positive Z. Then the part that goes up in the camera, I think for these planes, it's not. Let me turn off this rotation just to check something. I just want to see the texture. All right, so the upside of the texture. Okay, so this is weird. The upside of the texture is minus Y because Y is pointing down at the texture. So I need to invert it. To invert a vector, you just multiply it by -1. So it's minus Y, and its right side is X. You gotta remember these. So its front side, the thing I want to face the camera, is positive Z. Then the right side is X, and the top side is minus Y. So that's why I set these numbers in my node here. These are kind of crazy, and that's why it took me a while to figure this out. let me show you something. If I create a vector here, the points at x, and then I transform it from view space, which is the space of the camera, into world space, I'm gonna see what Unreal considers to be the right side of the camera. So if I preview this, now the right side of the camera is red, which means it's pointing at the x-axis. If I rotate this, now relative to the world, the right side of the camera is pointing to y. So x is the right side of the camera. Y. Now that made sense, right? Now this is gonna be crazy. Y for the camera is up. So the up of the view is being now the up of the world. So this is blue because this is Z. If I point green up in relation to camera, so now Y is up in relation to my view here. You can see this is green. So I'm always pointing here at the up side of the camera. So up in Unreal is Z, but for the camera, up is always Y. You gotta remember that. That's gonna be important. And Z is the direction the camera is looking at. So now Z, if I make X go in the direction the camera is looking at, you can see this becomes red. If I make Y going Y of the world, go into the direction that the camera is looking, this becomes green. And if I look straight up, I'm looking at Z, so this becomes blue. So Z is the front of the camera in the view space. So why am I telling you this? Because this is important on how you set up this material. You gotta remember that these X, Y, and Z coordinates, that's not written X, Y, and Z, but that's what they are the X, Y, and Z of the camera view. So X is what axis of your mesh you want to be aligned to the X of the camera. And remember, X of the camera is right. So here, the thing I want to be aligned right to the camera is X. So X in the plane. So that's gonna be, I'm gonna use X as the coordinate for the X on my camera. Now, Y for the camera is up. So what do I want my mesh to face up? Minus Y, because down is Y in my mesh. So I want minus Y to face up. That's why I set this to 0, minus 1, and 0. Alpha here doesn't matter, okay? Ignore alpha. So 0, minus 1, and 0. And finally, what I want to face the camera is Z. But the camera is looking at is positive Z. And this Z in the mesh is going against the camera. So it's minus Z. So that's why my coordinate here is 0, 0, minus 1, minus Z. That's how you make the mesh face the camera. You have to know what axis you want to be the forward vector, the up vector, the right vector, and then use those in this node. And then you use world position offset in your material world position offset, and then the rotated normals you input into the normal. And let me just see if these are tangent or world. Okay, so this is something that you gotta see. I'll just show you my inputs here so you can see my shortcuts when I do them. So this is world normal. That's what this material outputs. So you have to configure the material to expect world normals, not tangent. So you have to turn tangent space normal off. If you need to mix these normals with some normal map in your plane that's facing the camera or something that's following the camera, you're gonna have to convert this into tangent space. So you can do that with the transform node. This node is really useful. So I'm converting from world space, because this is world, into tangent space. So now if I make this material work as the default, this is gonna work just fine. And then I could mix this with normal maps. So if I have some normal map that adds detail, I could mix those, because these are tangent with a tangent normal map. So mixing them just work. But that's not what I want here, so I'm just gonna leave this to use world normal maps. All right. Now there's one caveat with this node that I'll show you how to fix. This plane without this material is with rotation 0, 0, 0. If you rotate your mesh, you're gonna see it doesn't match the camera anymore. And then you can think like, oh, the solution is just to keep the rotation at 0. But what if your actor is a child of another actor that is rotating and moving around the world? So you can't just make sure it's always gonna be at 0. So what you do is you fix this in the material. The bases are the direction of the material of the mesh that need to face those directions in the camera. If you rotate the bases with the rotation of the material, you fix this problem. So let's transform the axis that I picked from the mesh from local space into world space. I think that's I could be inverting it, but I think that's the way. So let's see. You have to set it to the 3-axis. Okay, so from local space, so whatever they are rotated, they're gonna become the direction that this node should change from the world space. So they're gonna rotate with the mesh. So if this works, my plane should be facing the camera no matter how I rotate it. So now it's working. So I can rotate my plane. You can see its rotation is changing. And it's always facing my camera. So even if this was a child of another actor that's moving around in the world, this would still work. Now, you can see that as I rotate, the lighting is changing. And that's weird, right? That's because I'm not fixing the normals with the rotation too. The way this node makes the math, it considers that the normals are not, they are in world coordinate. Or this is not the normals, this is the normals. It's picking the vertex normal from the mesh, and it considers that it's not rotated. But it is rotated, so we have to unrotate it. Now, to rotate these axes, we had to do local space to world space. To unrotate something, I mean, now that it's rotated, you need to 0 the rotation back. So to unrotate something, you just invert this. So you go from world to local space. Then you pass this into the normals. Fortunately, this node allows you to set the normals, the customized normals. And now, after it saves, now it's always making sense, no matter how I rotate. So now it's against the sun, it's backwards to the sun, and it's dark. And no matter how I rotate the actor itself, it's always dark. And if I rotate towards the sun, it's bright. So that's how you make a mesh always face the camera. It's a bit confusing, I know. Just to give a second example so it really fixes in your mind. This is the cone. I'm gonna make the cone follow the camera always facing right. So let's see, what are the axes that I need to set on the camera? So the right axis is going to be the blue axis from the cone. So let's see. I have those as instances. So I can just create an instance of my material. All right, so I created an instance of my material. I'm going to apply it to the cone. Now, let's see. We have to remember that these are X, Y, and Z of the camera. These vectors here, X, Y, and Z. So right view axis, that's why I named them this way. So right view axis, what do I want to be facing right on my camera? Z, so 1 here. Now my cone, these have to be perpendicular, so that's why the mesh is gone now. I have to finish fixing this. So let me get back to the standard material so that I can see the axis again. So I want Z to face right. I want X to face down, and in the camera, Y is up. So my up view axis here is gonna be minus X, because X, I want it to point down, I want to invert it. So it's gonna be -1. And the axis that looks directly at the camera is gonna be Y. And since the camera toward view axis is from the camera away, and this is going to be toward the camera, I have to invert it. So it's going to be -1 on G, which is Y. And if I apply this, it's not working. Let's see if it's because it's rotated. No, I did something wrong here. It's interesting because it is rotating with the camera. Right view axis. Wait a second. RGB toward view axis. G, if I remove this material, this would be Z, right view axis, Z, then toward view axis, -1 on green, and up view axis, -1 on red. Interesting, this works for the plane, but it doesn't for the cone. I'm curious. I tested this. Did I plug these wrong here? Right view axis, up view axis, toward view axis. Nope, they're plugged correctly. Okay, I'll have to figure this one out later, and I'm surely gonna make a tutorial on exactly how this works. I'm just guessing values now here. I'm not really thinking about them. All right, so this is how I wanted it to face, but it doesn't make sense to me now. All right, I'm really gonna have to make a tutorial about this once I figure this 100% out. I thought I had figured this out, and obviously I didn't. Okay, so I have something else in this level that I want to show you. So you might have faced this problem in Unreal before. Let me simulate this. So when you scale a mesh in Unreal, you can see from the shading of the mesh that the normals are not being fixed together with the scale. They're not changing with the scale. When you have something in real life, like let's say you have a sphere and then you squash the sphere, it becomes planar on both sides. But these left meshes here, as you can see, they don't look like they are becoming planar when they are squashed. The sphere there, where's my, here. The sphere there still looks round, but this one looks planar. Like this one looks like it's supposed to look. Same as this cone here that now looks like a plane, and this one doesn't. This one still looks like it's round, and same for the cylinder. So with materials, you can fix how the normals look after the mesh is scaled. You can fix this. And the way you do it, it's very simple math. You just get your vertex normals and divide by the object scale. I'm getting the object scale by vertex because I don't need it to be by pixel. But that's all you need to do. Divide the normals by the object scale and put that into the normal. Now this is also going to be in world space. So you need to make your material accept world space or convert these normals to tangent like I showed before. But that's how you fix it. So now when the mesh is scaled, you can see that it is changing the normals to look like a plane, to look like what the shape tells it should look like. So that's another thing you can do. Fix normals when you scale the mesh. All right, now the next one, shadow pass. This is something that I find really cool. You can change how the mesh is rendered in its shadows only. You can move the mesh in the shadows only, so you can change, you can make, like let's say if you know the math, you could make a cube look like a sphere in the shadow. What I'm doing here is I'm replacing the opacity of these meshes. They're masked meshes with opacity set to 1 always, but in their shadows, I'm using the texture here, this checkers texture, to set the opacity. And on these two in the front, for this one, I'm doing some math with the direction of the light, and then I compute if it's something that's facing the light, it's transparent, and when it's not facing the light, it becomes not transparent. So it creates this kind of a caustic effect here. And this is only beautiful for spheres. It doesn't really work with other meshes. It's weird because you just have one face made kind of transparent, the other not, so it's not, doesn't look cool. It looks cool with spheres. But it's in the shadow. Like I can move the object and the shadow is always going to be like that. And for the cube, I'm making a gradient that's opaque at the bottom and transparent at the top. So that's why you have this in the shadows. You have this gradient transition from bottom to the top. And the way to do it is you use a shadow pass node. Let me show the other one first, the texture one. Because these are 3 different materials. The one for the texture, the one for this gradient, and the one for this caustic effect. So you have this shadow pass switch. This is something that it says, when you are rendering shadows for this object, I want you to use whatever is in the shadow input. When you're not, use whatever is in the default input. So for this mesh, for this material, what I'm doing is when you're not rendering shadows, when you're rendering it for the camera or something like that, use 1 as opacity mask. So it's always opaque. But when you're rendering shadows, use this texture as opacity mask. So that's why you have the shadow looking like this. And this is just the transformation I was doing to rotate the mesh on the other material. So all that matters here is this. The shadow pass switch knows what you want. For the other 2 materials, this is the same material, this is the same material. Now for these here, I also use the shadow path. I just change what I send to the shadow input. So for the cube, I'm getting, let's use a cube here. I'm getting its world position, the size of the object bounds, which is a very high number, so it just looks like white. I'm dividing them, so I get values from 0 to 1 all across the cube. So it's a gradient with the size of the cube. So if I filter here, just the red color, you can see that on the red direction, I have a gradient from -1 to 1 here. So that's why it's 0 in the middle, and Unreal can't display negative colors, so that's why it's black on the left. Then I'm scaling those values with constant bias scale, with the values of 1 and 0.5. Constant bias scale, add the first value, and then multiply by the second. So I'm adding 1, so -1 to 1, plus 1 becomes 0 to 2. And then I'm multiplying it by 0.5. So 0 is still 0, and 2 times 0.5, which is the same as dividing by 2, becomes 1. So I have the range 0 to 1 on all axes. Then I'm filtering only the blue axis, which is the Z axis. So I have this gradient from bottom to top. I'm using 1 minus to invert what's 0 and what's 1. So I invert the gradient, and I use that with Jitter Temporal AA. Jitter Temporal AA is a node that's already in Unreal that creates this only black and white dots pattern, but randomizes these dots in a way that they become kind of blurry and it looks like a perfect gradient. You don't see the dots really well. You can see them. I don't know if you can see it in the screen, in the stream, but you can see you kind of see the dots. But it's very good for these kinds of effects, where you need something to be either 1 or 0, and you want to have like a gradient. And since this is a masked material, not a translucent one, opacity is either 1 or 0. So that's why I'm using this effect here. And I just used random to have these dots more randomized. And you have to set it to 1 to do that. And then I pass that into the shadow pass switch. So that's why my shadows look like this gradient, which is opaque at the bottom because I have white at the bottom, black at the top. So that's why it looks opaque at the bottom and transparent at the top. And for the sphere, it's just a different bit of math, but still using shadow pass switch. So for the shadow of the sphere, I have a light normal. It's something that I just use to tell what direction the light is in. This is not automatic because it could have any number of lights in the scene. So this is not something that you can do automatically. You have to create the normal yourself and set it. Then I normalize this to make sure it's a normal. It's just a direction with size of 1. It's a vector with size of 1. Then I dot with the pixel normal. Dot is something that outputs -1 if the thing. So this is the direction of my light. This down here. So all the normals that are pointing at this direction become 1 because dot is if two vectors are pointing the same direction, the result is 1. If they're pointing perpendicular to each other, it's 0. And if they're pointing completely opposite to each other, it's -1. So that's why you see here 1, then the transition all the way to 0, and then on this side it's negative. So I'm doing dot. Then I consider all the values from dot as positive. So both sides here are positive. Then I invert it to have a white in the middle, 1 in the middle, and black at the sides. And this is these are values from 0 to 1. Then I'm converting them to a range that works better with jitter temporal AA. I'm multiplying them by 2. Actually, I did some testing here and I ended up with these numbers. Now I realize that I can just multiply by 2 because that's all I'm doing there. 2. So I'm multiplying this by 2 just to have my jitter temporal AA make everything more white at the borders to get to white faster, but still almost black in the middle. And then I saturate those values just to make sure everything is between 0 and 1, because that's what saturate does, it clamps. And I pass that into the shadow pass switch. So in my level, I set this vector in the material. Let me see where it's here. So I set this vector here to something that was roughly in the direction of my light. I can change it here, you see, so I can rotate it. It stops working because my light's not really there on the other directions. So I found the direction of the light here, and I have this effect. Now for my next trick, multi-shader models. This is something that's kind of new in Unreal, so I realize most people don't know about it yet, but it helps with performance. Let me show some stats here again. So stat, scene rendering. So I have, how many do I have here? I have 114 of these windows here in my level. And as you can see, let's see if I can find the position again. As you can see, they are being rendered as they're being rendered with about 160 draw calls. And this is with Unreal optimizing them. So Unreal knows they're all the same mesh with the same materials, so Unreal is batching the calls. But still, it's a lot of draw calls. And each of these meshes, let me show you the settings in the mesh. They have 3 materials, one for the window, one for the wood, one for the glass, one for the wood, and one for these spheres here. And there are 3 different shading models. One is translucent, the other one is a default lit, and the other one is the car paint material, the coated, double coated material. So before, you would have to do it this way with 3 different materials. But now, with Unreal, since, I don't know, since 423 or something, it's not super recent, but it's recent, you can use it in a different way. You can have several materials in a different way. So let me replace all the windows with this model here. My draw calls went down a bit, so now from 160 they are 140. If you had several meshes that are not the same, Unreal wouldn't be able to do this optimization that it's doing. So let's simulate if you had that, like let's say several characters with a lot of materials in them. So I'm going to disable this optimization. It's r dot something dynamic instancing. Let's disable it. So if I disable this, imagine that each of these meshes are a completely different mesh with different materials. So they would be rendered as 488 draw calls, 488 draw calls. If I was using the other mesh that has the 3 materials, this one that I just put here, it's not 3 materials, it's only 2. If I was using the other one, this jumps up to 840 something calls. So let's go back to the optimized mesh, and I'm going to show you how it was optimized. So you see from 800 something to 473. This is the mesh that's optimized, and it only has 2 materials. I wanted it to be a single one, but the new feature I'm going to show you is still limited between translucent and non-translucent materials. So the non-translucent materials, you can merge them into a single material. And this is how you do it. Material, multi-shader. So this is my material. I set the material to use material attributes. So instead of having all the separate outputs, I have just one that's a full material, and I'm blending materials that I created inside of functions. So this wood function is a normal wood material with the wood textures here, roughness, normal, etc. But the thing here is the shading model. I'm setting the shading model to default lit. So you have this new node, shading model. And then you can choose what shader you want to use with this. So I'm setting it to shader model default lit, and then I output it from the function. So my function is outputting a material with default lit, and my material is set to use shading model from material expression. That's the key of the trick here. You have to set your material to use from material expression instead of one of these specific shading models here. And then each of your materials that you're blending in your final node, in your final material node, can set their own shading model. And you can do that with a texture mask, for instance. You don't even have to do full materials. You can have the same thing on all outputs, like I could have a standard material here, do everything normally like I would do, and change just the shading model using some texture as a mask. But here, I'm changing the whole material with the mask, and this is the mask. So this is really simple. I'm using only the green channel here, which is where I painted a mask for the spheres. Just say, hey, where the masks for the spheres is white. So if I multiply this just by 1, so you can see the value, you can see that it's white only here, which is where the UVs for my spheres are. You can see the material only on that part, and it's different shading model. So you can set that by pixel. You don't even depend in triangles as you would with different materials. You can set the shading model by pixel, which is super cool because it's super precise. Something that you might notice here is that this texture, actually, let me get, no, this texture is good. If I show you this texture, you're gonna see that where the sphere would be is still used by wood. So the UVs I'm using for the sphere and the UVs I'm using for the wood are not the same. And that's another something you can do in Unreal and use that in materials to your favor. This texture is using the default UV of the mesh, so UV 0. The const coordinate here, 0. But these here, I set them to use coordinate 1. So I'm using another UV set in my mesh. So I did it in Blender, and I did 2 mappings for my mesh. The first one is the one I use for the mask. So I say here's wood, here's glass, and here's the car material. And then on a second UV channel, I have all those things occupying the whole texture, but each separate material is occupying the whole texture. So I have all my wood parts occupying the whole texture. I have my 2 glass pieces, the front and the back of the mesh, occupying the whole texture. Focus. All right. So I have the both sides of my glass occupying the whole texture. It's these squares here that's really hard to see here. And also the spheres, these things full of vertices, occupying the whole texture. And that's because since I'm changing what materials and what textures I use for each part of the texture with this mask that uses the first UV, I can set textures that use a different UV for those parts that are being masked. It might be kind of confusing, but once you do it the first time and you have problems or not, if you understand it the first time, but once you do it and you have some problems, you're gonna understand what's going on and how you can use different UVs to your favor. This is very useful. I did it other times to do stuff like I had a spaceship and then I had lights around the spaceship, and I had a math in the material to do something that just had a white band going through the texture on horizontal. And I wanted the white band to be lighting up these lights. And the way I did that is I had the UV for the whole mesh, and then I had a separate UV just for the lights, all separated in the horizontal of the UV. So when I passed this white band through the UV, it would be lighting up those lights one by one, because there was one UV set with all of them straight out. I could do that in a single UV set, sure, but I had a different mapping for painting textures on top of the lights and everything else, so I needed to do a second UV just for the lights. So that's something that you can use to optimize, because now instead of every material you have in your mesh creates a draw call. So instead of having 3 draw calls per mesh here, I only have 2. And that's why when I change it back to the other mesh, you see the draw calls going up really high. And that's because you're not drawing once more for every mesh. You're drawing twice more for every mesh, because the light also has to draw every material. So you're drawing once for the camera, once for the light. And that's with one light. Imagine with more. Or render captures in your scene. Everything that's rendering the mesh is going to render once more. So the less materials you can have, the better. For instance, those meshes on Paragon, I remember one of the characters had like 7 materials. And this didn't exist back then. Now that it does, they could have done those meshes with less materials, way less draw calls per character. Right, so the next one is color masks. So this is a texture I'm using as a mask, and you probably know how to use one of the channels each as a mask. So for instance, I could use the red as a mask, the green as a mask, the blue as a mask, and the alpha as a mask. But what I'm doing here, that limits you to only 4 different masks, because it's only red, green, blue, and alpha. What I'm doing here, I'm using each different color as a mask. So I have this material here. Also, let me get rid of this text there. So I have this material here. And I've set up different settings for every layer. So I have the base layer, could be red. And then I have parameters. I have all the parameters in a single vector parameter. So metallic, roughness. I could make the roughness 0. So now this base is shiny. Can zero out the metallic so it looks like plastic, etc. Can make it emissive. And I can do that for other layers. Now, my other layers are set by colors. So whatever is white, yellow on that texture, which is its bottom corner. So its bottom corner is yellow. That's where it's gonna become this material on my mesh. So you can see my parameters here are emissive 100%. So that's why it's lit up. It's blue. I could make it, let's say, green. I can make it zero emissive, etc. And I can set these for 3 things. So I can mix up 3 different materials just using those color masks. So let's say I want to use blue here. So I know blue is red 0, green 0, P1. So now I'm using the top part. And because I have a blurry texture, I can also say if my mask should use the blur as kind of a transition. So I have this fuzziness parameter here. So if it's 0, it's like it is the material or it's not. There's no in between. If I increase this, there are in betweens. So I can blur this. I also have this expansion, which I can grow. Like how much of the difference to this color do you accept as mask or not? So for instance, if I put it to fuzziness 0, I can grow it while still having 0 transition at the borders. But then it starts to bleed into other colors because gray in numbers is similar to blue. And I'm going to show you why I say in numbers because of the way I'm doing these masks. So I have 3 of these. And the last one is using black. So it's this corner here. And let's see, color is this. It's probably, yeah, it's metallic. That's why it's just reflecting black there. So if I put it 0, it's not metallic anymore. Then I can make it emissive. All right, let me show you how the material works. So again, I'm creating some materials like I did in the functions, and then I'm mixing them up and passing it to the material as a material attribute. Then I blend them, etc. I could blend as many materials as I wanted here, one for each color if I wanted. The way you do the blending is you get the color from the texture. You have to think as colors as locations. So a location in a reel is an XYZ coordinate. So if you select an actor, you have the XYZ coordinate of the actor. Colors are also 3 numbers, R, G, and B. If you think of these 3 numbers as locations, you can compute the distance from one location to the other. So I can measure how far is one color from the other. And if they are very close to each other or they are at zero distance from each other, it means they are the same color. So I use that data as a mask. So what I'm doing here is I have a mask, the color that I want to use as a mask. So in this case, it's black. Then I measure the distance. Let me show this here. Then I measure the distance from black to the colors here in this texture. So if I preview this, you can see that the distance from black is 0. And to the other textures, it starts to increase. So from gray, it's kind of 0.5, but it's not exactly 0.5 because it's like a linear distance from one color to the other. And then I subtract the amount of expansion that I want. So I subtract from the computed distance. So let's say 0 here, 1 here. If I subtract, you're going to see everything starts to become black. So I'm expanding this mask. It's black only here. If I subtract these values and they start to become darker, you're going to see the mask starts to expand because right now the mask is the black part. And if you're reducing numbers, they go closer to black. So I'm expanding the black part. Then after the expansion, I compute the fuzziness. And the fuzziness is like, I get the distance and I divide the distance by how much of a transition I want. By default, I set it to be kind of low value. So I have only 0.48 of variation to do this transition. So let me show you. I'm dividing this transition value, so this distance value, by a certain number, and it's going to make everything that's 0, so everything that's black is not going to change. Everything that's 1 is going to be divided. I mean, any value greater than 0 is going to be divided by this fuzziness value. And I'm just making sure it's always above 0 because, you can't divide by 0. That doesn't exist in math. So I'm just making sure that if the user inputs 0 here, and type 0 manually, it's still counted as max 0001. As 001, because max is just what's the highest value. If this is 0, the highest value is 001. So I'm just making sure this is never 0. Then I divide my distance from this value, and now that I'm dividing it by a very low number, I have a very small transition, so it's invisible. You can't see the transition unless you can infinitely zoom there. So that's how I control the fuzziness. I call the fuzziness because that's how you say it in Photoshop, but it's the size of the transition from the mask to the rest of the texture. And then I invert these colors, so black becomes white and white becomes black, or darker colors. And I saturate it. Let me reduce the fuzziness because right now I'm interpolating to colors that are not exactly black. And I saturate just to make sure, because I subtracted here. When I subtracted, what was already 0 became negative colors. And this can affect an interpolation node. So I'm saturating just to make sure all my values are from 0 to 1. There's nothing smaller than 0. And also the distance between the colors could be higher than 1. So I'm clamping that as well. So saturate is clamped from 0 to 1. And that's how you do the mask. So first, you measure the distance from the color that you want to use as mask from the colors in the texture. And that alone just already creates a mask. Then you can do some math to expand and change the fuzziness. Then you have to invert it in order to make black become white and vice versa. Clamp to make sure everything is from 0 to 1. And use it to blend materials. Use it as the alpha to blend materials. I learned this technique not to blend materials, but to blend normal textures. Because when you do a character and you want the character to have those animated wrinkle maps, so for instance, the character is neutral like this, and then he does this, you want the wrinkles in the forehead. In order to do that, the lightest way is to have one single texture, one single normal map, besides your standard normal map, one single separate one with all the wrinkles. And then if you have a way to mask pieces of that texture to appear and disappear when you want them to, you can have just a single texture to serve as mask for every part of your face. So I did this to a character once, and I had something like, this part is red, this part is green, this part is pink, this part is some other color cyan, etc. And then I would change how much I want these masks. I would just multiply the final result here by something that could be from 0 to 1. If it's 0, I'm nulling the mask out. So I would multiply those masks by a value depending on the morph targets of the character. So if he was smiling, I would activate the wrinkles on both sides of the face with using those colored masks. And this was really useful because if you see tutorials about this, you might find those tutorials using the channels here as masks. But that limits you to only 4 masks per texture. So you have to use more textures in order to have masks for the whole face if you want to separate both sides. Because you could have wrinkles for the nose, wrinkles for here, wrinkles for here, all separate. So you need a lot of masks. If you do them with colors, and this way, you can have several. If you make the expansion 0 and fuzziness super low, or if you just say distance has to be exactly 0, so it has to be exactly that color, you can use a lot of colors because they won't bleed on each other. You're not accepting variations. And this is super useful to have several masks in a single texture. So this was this trick here. It's almost over, I swear. This is something I call localized post-process. Have you ever wanted to have a post-process that only affects the things that are inside the post-process. Even if you're outside of the post-process, you could see those things only being affected. I think a lot of people already tried that, and then they realized that it's impossible in Unreal because, I mean, not impossible. I'm going to show you a way to do this, but with the post-process volume, you can't do it because post-process volume affects what the camera is seeing when the camera is inside the volume, or if you make it infinite, it affects the whole world. There's no way to see it affect something when you're outside the volume and affect just the area. So there's a trick to do something like that. I have a sphere here with a special material, and this material, as you can see, is causing a diffraction effect. Increase the intensity here. So it's causing this diffraction effect only where my sphere is. So if I shrink this sphere, if I scale it down, you can see that only where this sphere is gets affected by its effect. And there's like a fade on the borders of the screen, so the effect fades out. So this is a translucent material. The way to do this kind of effect is you have to create a translucent material. This is not a post-process material, it's a standard surface material. Then you make it translucent. I make it unlit because I'm not going to need the shadowing in the material, so I make it unlit because it's way lighter on performance. And then once you have the material set as translucent, you have access to all the textures that post-process have access to. So you have access to the scene color, to custom depth, to stencils, to everything that post-processes materials have access to. So what I'm doing here, I'm sampling the scene color. It could be the same one you use in post-process, the scene texture with post-process input 0. Could be the same one. Then I'm distorting its UVs, and from these distorted versions, I'm using only the red. I'm using from one of the distorted versions the red channel, from the non-distorted version the green channel, and from another distorted version only the blue channel. And then I'm merging those. Let me see if I can preview it here. Oh, unfortunately, I can't. Yeah, you can't preview the results here, which is really sad. Actually, I think you kind of can, but it's too bad. So I use the screen position. Screen position, remember, it's the UVs of the screen. So if you want to map something to the screen, which I want because I'm getting scene color, is whatever was rendered before your translucent mesh. So I'm using that as a texture on top of my mesh. I'm mapping it to the screen, so I'm getting the what was rendered on the screen and stretching to, let me see if I can do this in the camera, and stretching it to the screen itself. So it's just getting the texture, getting whatever was behind this object and rendering exactly where it was before. But I'm distorting the coordinates that I used to sample from it. If I didn't, I would just be rendering the scene on top of my mesh, and it would look like my mesh doesn't even exist. And to make that effect of the material fading away at the borders, I'm using a Fresnel effect, inverting it to make it black on the sides. Then I multiply it also by the pixel depth, because pixel depth is darker as you get closer to an object. It's the distance from the object to the screen. Dividing by 100, so I have this fading in out when I am 1 meter away from the mesh or less. Then I saturate to make sure I have no values higher than 1. Multiply by the Fresnel, so I have the Fresnel and the fade out when I get close. And I multiply this by the amount of diffraction, which is what I'm using to decide how much I distort the UVs from the screen. So, and this one I'm just inverting the direction I distort to, just to have the blue channel going to the other side. So when I get close to the mesh, I also have this effect disappearing. So you don't see it disappearing suddenly when you go through the mesh. And just to show you the possibilities here, I did a second material that darkens things behind it and desaturates. So it's kind of a noir material. And it also has another effect that I didn't do on the other sphere, that it fades away the opacity of the effect when the mesh is going through other meshes. So the closer it is to other meshes, the more transparent it gets until you can't see it anymore. So the transitions move around its borders when it's going through other meshes. And you do that pretty easily. There's a node in Unreal to do that. It's called depth fade. So depth fade, you set what's the fade distance, like how far should the fading start. So I'm doing it 1 meter, 100 centimeters. And I'm using all the same effects as before for now with pixel depth, etc. I'm just adding depth fade to the math. So I'm passing that opacity that I already computed into the opacity for depth fade, and depth fade is gonna make things more translucent when they're close to other meshes. And then I have my effect here, so I get the texture from the scene, the things that were rendered before my translucent mesh, desaturated, multiply by the amount, the saturation, the fraction of the desaturation is the amount I want, times the amount of the effect I should have. Then I use a lerp here with the amount of effect I should have also as a, like when it's 0, I have 1 for the power, because power darkens things. So if this value is 0, I put 1 here. 1 doesn't change anything when you use power. It's like a number powered to 1 is the number itself. And if it's 1, this is the value that comes from here. If it's 1, I powered it to 3. So this is just to darken the scene. And I output it to the emissive color. I also output it to the opacity. And this is to show you something that's kind of a limitation. So if I try to mix these two materials by putting one in front of the other, it doesn't work. You either see one or you see the other, whichever Unreal decides that is in front. And this is because these are not really transparent things. They're translucent materials, but they are opaque with the scene applied to them as a texture. So it's like an opaque mesh with the scene texture on top of it. So they're not really translucent. So that's why you see one or the other. If you change, like you can see, I can see a bit of the diffraction of the material below it, but that's because the top one, I did opacity to it. So it's like, you can see the effect mixing a bit, but you're not darkening. Let me put the other one in front of this. I can't select it because the second sphere is on top of it. All right. So you're not actually distorting. As you can see here, I'm distorting the normal colors from the scene, not the darkened ones from the mesh. That's because the texture I'm using to distort is what's being rendered before translucent meshes. It's not what was rendered before this mesh. So translucent meshes are rendered separately after all the opaque meshes. And you can read the texture of that render in your translucent meshes. But your translucent meshes can't read the translucent meshes behind them. So that's the limitation. You see either one effect or the other, or you do some opacity, but you're not actually affecting the effect that was already applied behind you. Now for the second last one, I have post-process for widgets. So if I play this, you see I have my widget and I have this crazy shadow effect going on. And I can change the blur size of my effect. So I can make it really blurry. I can make it not blurry at all. I can have an offset for my shadow. So it's like a drop shadow effect that I created. And how do you apply post-process effects to widgets? Let me show you, because this is really cool. In your widgets, you can make your widgets children of a widget that's called retainer box. And the retainer box is an optimization widget in Unreal. You can set it to render only like once every 10 frames. And you do that by configuring these phase and phase count settings here. So you can have your widgets being calculated to render less times. If the widgets are not moving at all, you can have this optimize your widgets a lot. So you don't waste performance on things that are not moving in the screen. The bonus of having this widget is that in order to have something not being rendered every time, it means that these things have to be rendered into a single texture, and then this texture is showed on screen instead of the widgets being rendered every time. Having a texture that's showed on screen, that is displayed on screen, means you can put that texture in a material and apply effects to it before it goes to screen. And Epic Games was really cool because they made it possible to do it with the retainer box by using an effect material. So you create a material, you create a texture parameter in it with the name that is here. So texture parameter, it's named texture here. You can change this name if you want. So I left it as texture, it's the default. So in my material, I have, this is the instance. In the material itself, I have this texture parameter here. And then before, this is, of course, this has to be a user interface material because it's going to be used in the interface. And the blend mode is translucent if you want to keep the transparent things in your UI, which you probably want. So you can get the texture and just display it as it is, or multiply it by some color, etc. What I'm doing here is I'm passing this texture through a custom node that creates a blur effect. And this is something I got from Unreal itself. I just modified it to do a few things different with the alpha channel. But Unreal has a blur spiral blur texture node that you pass a texture to it, a texture object. So your parameter has to be a texture object, not a texture sample. So when you create a texture parameter, you can have a texture sampler parameter here. Where's it? Texture object parameter or texture sample parameter 2D. This is the standard one texture per parameter. When you only sample it, you sample it directly in the parameter, or you can use a text object parameter, which allows you to sample it several times. And that's what this node does. It samples that texture several times to blur it and compute the blurry version of it. So I'm using that with some things to change colors, etc. I mean, how I created this effect is not the cool thing here. Might be for some, but the cool thing is that you can apply effects to your widgets. So this is really cool. Once I have this tutorial on my YouTube channel too. You can make it look like your UI is underwater if you get that texture and just start it using a normal map for water. So if you just start the coordinate UVs with the normal map, you can and move the normal map around, you can make it look like the UI is underwater, just starting. So you can do lots of things. And I used it to do this drop shadows effect because many times I wanted drop shadows in the user interface, and that's not something that's already there. But since you're allowed to apply any material on top of your user interface before it goes to the screen, you can do these effects now. And the last one that I have for you is what you can do with render targets. So let me show you this. This one I didn't do from scratch because most of the math still goes over my head. But I want to show you the possibility when you have render targets. So I got this from the content examples from Unreal. And what this is doing is there's a plane, and every time you shoot at the plane, you click in the plane, it traces the point from the camera to the plane, and from the hit, it gets the UVs of the hit in the plane, and then it paints in a render texture those. I'm gonna have to show you because it's a lot to say. Where's it? Force splat. So there's a material that's like a brush. They draw sphere. Wherever you say draw sphere here. So there's a sphere in this material. and they called it force position, the position of the screen, the sphere. So it's currently at 5.5. If I put it at 1.1, you're gonna see that it appears in the corner of the box here. Let me see if I can just preview the opacity. So you can see the sphere is right here at the corner. So let me put back to the center, which is the default. So they use this material to render that into render targets. So they have 2 render targets. They render this into one of those render targets. Then they have a second material that does the height simulation. And this is probably the one with math that goes over my head. Let's see. No, that's not the one. Where? Height field painter. No. Compute normal. It might be... No, this is just computing the normal. I can't find the material that's doing the water motion. Travel speed. I think it's this one. But the trick is they have 2 render targets. They draw the splat of when you click in the water into one of the render targets, and then it passes this render target to a second material. This material simulates the ripples from that splat location, and they render this material into another render target and use that final render target to generate normals and use those render targets as textures, a height field and a height field normal in the water material. And they do that in a blueprint via a node that's the key thing to the trick here. Where is it? No, I don't want the draw canvas. I want the simpler one. Draw material to render target. So you pass the render target, you pass a material to it, and then you can draw a material directly into a texture, whatever you put in your material. And that's really cool for many things, because if you create some effect, if you do something that's let's say it's really heavy, like a noise texture that takes a lot of performance from the GPU, you can render that on a render target. Then you can right-click the render target and choose create static texture. So you create a texture from that effect. For instance, when I'm simulating, I can do this, etc., etc. Now, if I look at the render targets here, these colors must be negative. It's transparent. The water's probably settled already. Let's see if I can make it show up. It's not showing up. What if I do this? It showed up now. Okay. So as you can see, everything I was doing there has been drawn into these textures. And then I could right-click even the normal one that was being calculated in real time. I can right-click this and create static texture. So now I have a texture that is that effect. So this is one of the usages you can do to render targets. You can draw complex stuff onto them and then convert them to permanent textures in your project. Or you can do what they are doing here, which is awesome and still goes over my head. You can draw the height of a point. They do point damage here. So on tick, they trace. Where's the damage? Trace, set vector, set scalar, direct target. Compute normal, apply fluid simulation kernel. Where's the trace? I remember I saw the trace here. Overlap to save the character. I think the trace is in the pawn. Where's the pawn? I'm gonna take forever to find this. But the pawn, it makes trace. And then when it traces the plane, it applies damage. And then when it applies damage, they get the hit location. From the hit location, they compute the UV that was hit in the plane. In the plane, it's easy to find the UV because it's just a plane. So you compute where the coordinate is between the start and the end of the plane. So they pass this to the material using set vector parameter value. So they get the material here, they create a dynamic material instance from the original material, set vector parameter value from this UV coordinate. This is the material force split. So this is that material that I showed you that does, that does the painting of one single point of force. So they apply this force with a white color. And from that, they pass this render target where this material was rendered to another material that computes the ripples. And this is one of the things you can do. You can do many things by drawing render targets in materials. You can like blur something super fast, because blurring things with the GPU is fast if you know how to do the math, or you can use the spiral blur texture node I showed you from the engine. So you can do all that by drawing materials in render targets, then use those render targets as texture for something else. So this was it. This is the end of this presentation. I hope you learned something new. I am sorry for the times where I got confused, because, you know, I wanted to talk a lot about a lot of things, and you always get confused with the amount of information. But I hope I taught you something new, and that you had ideas to solve some material problem you were having in your own projects. And I'll be back someday with more techniques. Oh, just one thing that is very important. The shadow pass thing doesn't work in ray tracing. Ray tracing doesn't allow you to change the shadows of your objects. So it only works when you're not using ray tracing. And the mesh transformation thing in the material, if you want to see the mesh rotating in reflections, etc., when you're doing ray tracing, you need to enable, where is it? Use a touch, visible, no, ray tracing. Here, in ray tracing, you have to enable evaluate world position offset. It's on rendering, advanced settings, ray tracing, evaluate world position offset. If you don't do this, you're going to be rotating your mesh with the material, but the shadows are not going to be rotating, and the reflections of this mesh are not going to be rotating. So you need to activate that in order for the changes you do to the mesh in the material to be considered for ray tracing, on ray traced effects. That's it. Hope to see you next time here.